In Chapter 6, Section 4, we move on to focus on our identities. Now, we just used in the last section the Pythagorean identity. So we've recently talked about that basic Pythagorean identity. And we know that there are two other Pythagorean identities that we solve for as well. What makes this an identity? One thing that we tend to do in our math classes is separate math from the English language, and we shouldn't do that. You know what the word identity means. Just like you have your own identity, it's what makes you who you are, and it should be who you are no matter where you are, right? Well, if we say an equation is an identity, then it is true that it is going to maintain its value for every input. For example, now it gives just a couple of examples of how you could confirm that our Pythagorean identity is going to be true for any value of theta. It gives you a couple of suggestions. It says, okay, what if theta is 35 degrees? Well, if theta is 35 degrees and our Pythagorean identity is true, then sine square 35 plus cosine square 35 should be 1. So let's do that. Let's look and see. Well, if I do sine of 35 and I square that, and then I add to that, and I'm going to put this in parentheses so I can square it, cosine 35, close all your parentheses, squared, and I hit enter, yep, I get 1. If I turned it into radian mode and I plug in 5 pi thirds and square each of those. Remember that when we are squaring here, we're squaring the function value. So you find the sine function value and you square it. You find the cosine function value and you square it. And then you add those two together. You're going to get 1 if you're doing it correctly in your calculator, no matter what you plug in. Now, we cannot realistically check every possible value of theta because theta can be anything. But they do give us a couple of examples that show that it works. Now, if I graphed all of these values of sine square theta plus cosine square theta, it would just be a horizontal line because all of the results would be 1. Now, we're not entering it into a graphing device. I know that you guys, most of you probably have graphing calculators. I know you all have access to graphing utilities online like Desmos. Those are fine and great and good to check things with. Our goal this semester is that you understand these fundamental foundational concepts for calculus. Next semester, when you're in Cal 1, your instructor is going to let you have that graphing calculator because the things we're doing this semester that we're working to make certain that we understand completely, we're not just plugging in values, those are going to be the givens that you're going to be using to do more complex computations with. So this semester, I want to really challenge you to not cheat on your homework and use a graphing calculator so that you are understanding these foundational concepts. The only reason to take PreCal is because you plan to work your way up through the calculus sequence. And if you're going to work your way through up the calculus sequence, it only hurts you if you don't put in the time now to make sure you understand the things that we're working on. Okay, I hear outside that my buddy next door has come back out with his weed eater. I apologize sincerely for that. Okay, so what makes an identity different from another type of from an equation? Well, an equation that is not an identity is called a conditional equation. We worked with conditional equations in college algebra. For example, 2 times x minus 3 quantity equals 5 is only true if x is 11 halves. Or sine of x equals 0 is only true if x is an integer multiple of pi. Those are only true under certain conditions. Our definition for an identity right here. 2 functions f and g are said to be identically equal if f of x equals g of x for every value of x for which both functions are defined. Such an equation is referred to as an identity. They are true for every value in the domain. An equation that is not an identity, that's not true for every value in the domain, is called a conditional equation. Now, when we work with identities, we're not solving, we're not working back and forth. And when I give you an identity and I say verify, I'm not asking you if it's an identity. I'm saying this is an identity. Prove it. Show me how. Okay, guys? Here are some identities you already know. We've already talked about these basic trig identities. We have two quotient identities for tangent and cotangent. Tangent theta is sine theta over cosine theta, and cotangent theta is the reciprocal of that. Then we have our reciprocal identities. Cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. And cotangent theta is 1 over tangent theta, where each function is defined as its reciprocal, in terms of its reciprocal. Now, remember that my angle, my theta here, I could have used x, I could have used alpha, I could have used any other variable. That is my argument. Do not leave off that argument. If you leave off the argument, it's wrong. Okay, Pythagorean identities. Sine squared theta plus cosine squared theta is 1. Tangent square theta plus 1 is secant square theta, and 1 plus cotangent square theta is cosecant square theta. Now, we developed these two companion Pythagorean identities by first dividing everything by sine square theta and then coming back and dividing everything by cosine square theta to get these two. They can be turned around and rewritten. For example, tangent square theta plus 1 equals secant square theta could also be written as secant square theta minus 1 equals tangent square theta by moving the 1 over, or 1 equals secant square theta minus tangent square theta. So each of these three can be turned around and rewritten in terms of one of the other pieces. Okay, and then we have our even-odd identities. Hopefully you remember that your even function is cosine and its reciprocal, so that cosine of negative theta is equal to cosine theta, secant of negative theta is equal to secant theta. Those are my two even functions. The other four are odd. And remember that when we were working with our inverse functions, that we did not extend this even function to cosine inverse. Okay, let's look at the next page. The goal in this section is to establish new identities by graphically manipulating algebraic expressions. Some techniques to do this will be demonstrated. So here's the deal. You do not automatically know how to verify identities. You need some tools in your toolbox. We're going to give you some tools in your toolbox. Verifying identities is still trial and error. You've got to just start somewhere and you got to work and see if it works, and if it doesn't, you start over and you try something else. But the more tools you have in your toolbox, the more things you have to try, the better off you're going to be. The first thing that we have to try, the first tool for your toolbox, is to multiply by a well-chosen 1. Now, we use multiplication by a well-chosen 1 to find common denominators all the time. On the last section, I think it was, I needed to add something like pi third plus 2 pi. This is not right. This pi third plus pi half. Well, if I need to add pi third and pi half, I need a common denominator of 6. I'm going to use a well-chosen 1 of 2 over 2 and a well-chosen 1 of 3 over 3 to get my common denominator. We are going to practice multiplying by a well-chosen 1 down here. It says to simplify sine theta over 1 plus cosine theta by doing the following. Well, we are going to multiply by a well-chosen 1. And in this case, our well-chosen 1 is going to be the conjugate of the binomial. Use the conjugate of a binomial. And you can choose a binomial in either the numerator, the top, or the denominator, the bottom, depending on what you need to do, where you're headed. But you're going to use the conjugate. This is a binomial because it has 2 terms. Bi means 2, right? Conjugates are the same 2 terms with a different sign. So the conjugate of 1 plus cosine theta is 1 minus cosine theta. I'm using it, that conjugate, as a well-chosen one. Anything over itself is 1. So we are multiplying by a well-chosen one. When I do that, my numerator that I get is going to be sine theta minus sine theta cosine theta. Don't drop your arguments. My denominator, anytime I multiply conjugates together, I get difference of squares because the outside and the inside products add to 0. So 1 times 1 is 1. The outside and inside add to 0. Cosine theta times a negative cosine theta is minus cosine square theta. So I have multiplied by a well-chosen one. I got difference of squares in my denominator. So what can I do next? Well, I'm going to apply my Pythagorean theorem. Remember that cosine square theta plus sine square theta equals 1. Well, I have 1 minus cosine square theta. So 1 minus cosine square theta then would be sine square theta. So I'm going to substitute sine square theta into my denominator. All right, now I see that I have sines in the numerator in both terms because I distributed that in. What if I undo that distribution? What if I pull that sine theta back out? So sine theta times 1 minus cosine theta. I put my numerator back like it was. Sine theta times 1 minus cosine theta. I still have sine squared theta in my denominator. Now I can simplify because I have common factors here. I've got sine theta and I've got sine theta times itself here, so that I have 1 minus cosine theta over sine theta, and that is completely simplified. Now, all I did was kind of rearrange some things, right? What I did was say, you know what, sine theta over 1 plus cosine theta is going to be equal to 1 minus cosine theta over sine theta. This didn't, it might have advanced me forward if it were part of a larger problem. Right now, what we are doing is practicing manipulating the terms. That was our entire goal here. All this was a way for us to practice manipulating the terms. That's important because you have to know what you're allowed to do, and you have to know what works algebraically with your trig functions. Another thing that you can do, another tool that you can add to your toolbox, in addition to multiplying by a well-chosen one, is to rewrite an expression over a common denominator. You're used to doing this in algebra. I've got 1 over 1 minus sine theta, and I want to add to that 1 over 1 plus sine theta. I can only combine these two terms using addition if I have a common denominator. Well, what's my common denominator here? It's going to be that difference of squares, 1 minus sine square theta, if I multiply these two conjugates together. To get that, I'm going to be using that well-chosen one idea, just like we did up here to create a common denominator. For the first term, I need to multiply in 1 plus sine theta over itself. For the second term, I need to multiply in 1 minus sine theta over itself. All right, so what do I get? My first term is 1 plus sine theta over that common denominator that we created. My second term becomes 1 minus sine theta over that common denominator that we created. I can combine that into a single term by writing it all over 1 minus sine squared theta. Well, what do I have? I have 1 plus 1 is 2, and then I have positive sine theta and a negative sine theta. That adds to 0. Can I simplify this any further? Well, yes, because this 1 minus sine squared theta, what would that be equal to? Again, remember your Pythagorean theorem. Cosine squared theta plus sine squared theta equals 1. I have 1 minus sine squared theta. That's going to be equal to cosine squared theta. So I can use that Pythagorean identity here, and I can say, all right, this simplifies to be 2 over cosine square theta. Again, we practice manipulating our terms with our trigonomic functions, reminding ourselves what we can do algebraically. What are some legal moves? Another thing you can do, in addition to multiplying by the well-chosen one, making sure you have a common denominator, is to factor, to remove common factors. We're going to simplify 1 minus cosine square v over sine v plus cosine v sine v. Well, I see in my denominator I have a common factor of sine. Can I rewrite my numerator in terms of sine? Well, numerator is difference of squares. I could rewrite that in terms of sine, right? So cosine square v is going to be the same thing as 1 minus sine square v. So if I do, 1 minus cosine square v. 1 minus cosine square v is sine square v. My denominator, let's factor out that sine v. I have sine v times 1 plus cosine v. Well, when I factor out that common sine v, I get sine v over 1 plus cosine v. That's one way to do it. Let me show you another way to do it. So you don't have to do both, but this gives one way to simplify. Another way to simplify would be instead of, so this is an or, instead of substituting here, I could factor. That's what I was told to do. I ignored my instruction. I'm so sorry. I used a substitution instead of a factor. Well, this is still correct. It's just not what I was trying to show you. This was what I intended to show you. Let's factor this numerator. Oh, I did factor the denominator here. Now we're going to factor the numerator. Difference of squares factors out to be conjugate pairs. 1 plus cosine v, 1 minus cosine v. We're still going to factor the denominator. Sine v times 1 plus cosine v. And you see that I have a common factor in the numerator and the denominator, so that anything over itself is 1. Simplifies, therefore, to be 1 minus cosine v over sine v. These two things are equal to each other, which, back up here in number 1, is what we found to start with. Sine v plus cosine v. I don't know if I can get them both on the same page. Yep, sine v plus cosine v right here is equal to 1 minus cosine v over sine v right here. So we got the same result using two different methods. Okay, final example for section 6.4 notes. In the example below, an equation is given and we want to establish the identity listed. We're going to begin on one side of the equation and manipulate it to arrive at the other side. Another word for establishing an identity is to verify the identities. When we verify identities, we are not going to move terms back and forth. It is not solving. You don't move things back and forth across the equal sign. Don't move terms across the equal sign. Okay? You're not solving. The method you're going to use here is to rewrite one side in terms of sine and cosine. So putting things in terms of sine and cosine is a great plan of attack for verifying identities. Typically, we start with the side containing the most complicated expression. We only want to change it. So the left side is more complicated. We're going to leave the right side alone. Notice we just have this equal sign. A lot of the times I will put a line down my page to remind myself not to cross that line, not to cross it, treat it like a brick wall. So on the left side, I'm going to go to terms of sine and cosine. Cotangent theta is cosine theta over sine theta. secant theta is 1 over cosine theta. Well, what can I do now? I see that I have a common factor in the numerator and denominator, so that leaves me with 1 over sine theta. And 1 over sine theta is the same thing as cosecant theta, and that was my goal. That was what I was after. That is how you verify an identity. You manipulate one side until it matches the other, if at all possible.